For the Anchor modeling tool, we devised a new type of layout algorithm. It's an interactive force-directed graph algorithm, and what we have done is to do away with the need to be physically accurate. Instead, we focused on getting something that produced a reasonably good layout without being physically accurate in order to do some performance improvements. If you look under the settings menu, you can see some of the different options that control the algorithm, and we can use this to understand it a little bit better. First, I'm going to toggle the debug here, and now you can actually see the resulting forces in the model. So for example, if you look at this edge here, you can see that there's a force here that wants to pull it down to the left. So if I press play here, you can see that it actually starts to move a little bit in that direction. So the model always strives for some kind of equilibrium. The damping here, that's a factor that reduces the total kinetic energy in the model over time with each iteration. So if I were to reduce this one to 1, for example, you can liken this with friction in a physical environment, and press play here, you can see that we get something that's taking much longer to reach an equilibrium and actually stop here. It almost looks like some kind of organism moving around on the screen right now. So I'm going to put the damping back to 4, and now you can see that it stabilizes itself quite quickly. The normal distance, that's the distance you would get in pixels between two objects in the model, if there were only two objects. So if I reduce this one to 20, for example, and press play, you can see that the model becomes much more compact. So you can play around with that yeah, if you want to. Then we have the stopping velocity. That's the lower bound velocity. So if something in the model gets a velocity below this level, then we assume that it has stopped moving. And currently we set it to 0.1 pixel per second. If you get below that velocity, then it will practically stop. We have a different starting velocity, so it takes a greater force to actually start an object that has stopped. In this case, if something is not moving a whole pixel, then we do not care about moving it at all. Then we also have a maximum starting velocity. This is due to the fact that if you have a large model, you will have more things that influence each object in the model. So in that case, when you get a larger and larger model, it will approach this starting velocity number. So if you have a lot of different objects, it takes a larger force also to actually start something in the model. We have a node influence factor. This is the distance that if you look at the single node here in the model, we look a normal distance away times this factor. So in this case we look 30 pixels away, and if something is not within the square here, 30 pixels away from this one, we do not calculate it as attributing to the forces in this on this node. So if I reduce that to 1, for example, and press play, not much is happening, but anyway, in this case we look at 4 normal distances away. We also have the edge stiffness factor. That's for the different edges in the model. So if you look at an edge here, those are the black lines connecting things. The stiffness factor determines if they behave like rubber bands or like a 2-inch steel wire. So if it's lower, then it's less stiff and more like a rubber band, and they will more easily bend. However, that can actually produce, in some cases you get some sort of like a gravity well, and in that case things can bend quite a lot. So that's short about how this works.